Hello, let's get started. So, yeah, Discover, I am also looking a bit weird. Okay, so yeah, I don't know why there's a shadow there. I have to maybe like figure out my lighting again. Yeah, it's not stable because I have a curtain. Like I try to put it always the same way, but it's not. Seems like it's not all the time. Maybe I can make it a little bit better by doing. No, it's not going better. Oops. Ooh. Okay. Right, okay, so I hope it doesn't cause too much of a shadow. And today, well, we are Legend of Data, and we are trying to um, go through the categorical data. And first things first, we are not coding today. We are just gonna create a discussion because I think that it would be good to save the deep dive for different episodes. So I'm just gonna go through the kind of introduction here, and next time like we could go through the algorithms like in more like details. Okay, so yeah, so let's crack on. And right, so well. This is the definition of categorical data. I would say that categorical data is actually very popular. Um, so yeah, like the definition is that it's a variable that is kind of is fixed number of possible values. um there are rare cases that sometimes you have to, it's like imagine you are creating a survey. Okay, so you have a multiple choice, so people have choices that they could put themselves into either one of the categories, but sometimes it's there is like the definition is a little bit vague because like you would have a box as others and so sometimes there's actually like infinite number of choices is still possible. So that's why we have the box others for categories that we basically didn't expect. So they are unseen categories in this kind of data, and it makes things like much more complicated to deal with. So it make this data much more difficult to clean and much more difficult to prepare for machine learning, and it may cause some problems as well. So number of possible, yeah. So it's like but in theory, it should be a fixed number of possible values. So you put different things to different boxes, and so you assign like each for each record. So they should be belongs to one of those boxes. Okay, so that's well, you're categorizing people or categorizing objects or categorizing situations. So you are like so there are different categories. So that's the official definition from Wikipedia. Um, Yeah, they're everywhere. Like I would say that I encounter them very, very often when I was working as a data scientist. A lot of the data that I deal with are actually categorical data. Is yeah, it's rare that you would have uh, you know have like pure numerical data on a on a spectrum and also predicting a numerical value. You would, but a lot of the times because you're writing an algorithm to help make decisions, so a lot of the time even like the final result you get is actually also a categorical prediction, um, rather than a so yeah, so it's either, so there's two ways. So either the features, the inputs are categorical, or the output actually we want categorical output. So yeah, so they are like actually two ways. So you're gonna try to talk about them together, like to have a kind of a discussion about it. But these data actually like are everywhere. For example, my friend is doing a project about like voting data. So like which party do the people vote? That would be something that you know they would be thinking about when they're doing like some research on the voting or election prediction and things like that. Um, which recycle material? That's also inspired by my other friend doing a project about like recycling materials. So basically, there she put a flow chart there that different recycling materials will go to different places. Um, so yeah, and well, for the recycling materials, you have plastics, you have paper, you have metals, and like you can put them into different categories. You can put them into big categories or smaller categories. So that's another things that you have sometimes have to think about. That for some, if the data that you got is like very fine, for example, different type of plastic, but maybe it's better if you group them into just plastic, okay? or you have different type of metals. You just aluminum can, different, like maybe you want to group them into just metal. Um, so yeah, like it depends on the cases. You may have to group the categories as well. Which country people are in. Again, you could also group by regions if you have to. So yeah, so they're everywhere in real life, and they're not easy to deal with. They're not not as ideal as the numerical data. Um, yeah, reason why they're so difficult to deal with is that because they are just labels. They are not. So a lot of semantic are carried in the word, or they're not numeric. It's difficult because in machine learning, machine understand numbers, and anything that's not numbers is super difficult to deal with. That's why NLP is so hard. It takes so long for people to kind of now start to have decent, bots that could talk to human in natural language. Yeah, it has been like for ages. If you look at some kind of documentaries in the 90s, and you see like there are bots that are hilarious that you talk over the phone, and like basically that the bot on the other end doesn't understand anything at all. Now it's like getting much better thanks to the NLP development. But yeah, so machine love numbers. Anything that is not numbers, that is difficult. So categorical data, they are just labels. They are difficult. They're not continuous. That's also another problem. Some algorithm doesn't apply to them because they're not continuous. And yeah, sometimes it's another tricky bit is that, well, you'll see later that for example, we want to label them. For example, we just give them 1, 2, 3, 4, 5, so they become numeric. But it doesn't make sense because, well, why? Let's say if you label men and women, why men came before women, or why doesn't women come before men? Like, what like the order doesn't mean anything. There's no order to the data, so why could you label them with order? Because like numbers, you can order them, right? And also their intensity. So there's like so much difference between the categorical things and numbers. So sometimes it's not equivalent. You can't just directly convert one to another. um, so one thing like linear regression, actually you don't want linear regression anymore. Reason because well, we have two ends to discover, right? So one thing is that when you have data coming in the linear regression categorical data, first of all you have to encode them. So when you encode them, you can label them 1, 2, 3, 4, 5. That's fine, but the order doesn't matter. So well, linear regression basically is looking at, remember the sliding game, right? The axis. So we try to formulate a line that explains the relations between the x and the y axis. Okay, so in general term, it's like we find a line in high dimension to relate the input to the output. Excuse me. Yeah, I don't know why like my nose is super itchy today. um, yeah. Uh, so so you can't find a line because like if the number, the input itself is the number that it represents, it doesn't carry the meaning, so then it's not really um meaningful for the input. Like on the other side, if your output you want to predict which category this thing will belong, but again, like it doesn't mean a lot because it's a line and you get a value back. Well, you can find a way to map the value back to a category, but again, it doesn't make a lot of sense. Um, so it's a big no. And logistic regression actually is kind of doing a thing that is dealing with category. The output of it, remember, is binary 0, 1. So binary 0, 1 actually is a special case of a categorical data. Okay, so because actually there's two categories, either 0 or 1. So um, yeah, so it's a categorical data. It's fine. But well, like I said, in real life, not everything is 0 or 1. We have different parties. Sometimes there are other like tiny parties, so there's more than two parties. Or like recycling materials. Obviously, you don't like you can't have just two materials. You have more than two. So for a lot of things, it's more than like just two categories. So so we have something called dummy variables. So when we're dealing with these categorical data, we have to changed our categorical data into a dummy variables. Okay, we have to change them into a number that we could use in models. So here is there's an example of regression analysis. So well, obviously you have to change that into a number, and yeah, so there are different ways that you can turn a categorical data into a number. And um, so one thing to do is like one hot encoding that well, I'll explain a little bit later. So one way of doing it is front hot encoding. The other way is label encoding. Okay, there are other encoding methods, but there are like drawbacks and different reason why it's not as popular. So um, so one hot encoding example. I have three categories: apple, banana, and orange. And what I can do to turn them into numbers is that yeah, I can turn them into like I create three more variables. So is this an apple 0 1? Is this a banana 0 1? Is this an orange 0 1? So if it's an apple, so it will be like 1 0 0. If it's a banana, it will be like 0 1 0. If it's an orange, it's like 0 0 1. So that's how you do it. The advantage of it is very precise because there's no ambiguity. It's just, well, it reflects the fact that is it an apple, yes or no. It's truly representing what it is. It's not like if you like do other things with it, like then it's a bit ambiguous. Because for example, if you like label 1 2 3, so is it one an apple or one is an orange? Okay, but this one is very certain that there's no ambiguity in there. But the problem is that, well, you can see that here originally I have one like one variable that what fruit it is. Let's say the variable was what fruit it is. So it could be an apple, banana, or orange. I only got like three fruit in my fridge. Okay, so there's only three. Um, but when I encode it, then I have three variables. Is this an apple? Is this a banana? Or is this an orange? So imagine, so now it's not just in my fridge, it's like in the world. So there's so many different type of fruits in the world. And if you have like many classes, so you have apple, peaches, banana, orange, and even like you have different species of apple. Let's say you're very like you're very want to be botanically precise. You have different species of apple, different species of banana. You have many classes. Then the number of variable you have is really big, and we don't want that because it will really expand the memory that required for your computer quite fast, and also it will you know um, expand, like it will also sometimes make the algorithm doesn't work well, because sometimes if you do regression in high dimension, then um, that like it would really make the model very sensitive. Okay, so you want to reduce, sometimes you have to reduce the dimension. So you are doing the opposite. You have to reduce the dimension, but now you're like expanding it so much. Usually expanding the dimension, expanding the number of variables is not good. So we don't want to do that. So what should we do? The other ways, there is label encoding. So so we use a totally different strategy. So like I said before, you can label them 1 2 3. Okay, one is apple, B is banana, 3 is orange. Um, is because they are alphabetically in this order. So, so that's my rule. I put them in alphabetical order, so 1, 2, 3. Um, yeah, but well, the good thing is that uh, the number of variables remain the same. I still have what fruit it is. It's just that instead of apple, banana, orange, I just change them into 1, 2, 3. Okay, so like if someone sees this number, if someone know the knowledge from me that I just put them in alphabetical order and there's only three types of fruits, then they know that, oh, if I see a 2, so there's only apple, banana, orange. Oh, it's a banana. Okay, so someone knows. um but so like the number of variables doesn't expand, but the problem is that like the order of the class is ambiguous. I chose the rule to put it in alphabetical order. What if someone put different orders, like if someone want to how many characters this word has, or someone use another language. So apple is not apple, it's something else. And then like the order of the alphabetical order will change. Okay, or someone label them with what are their favorite, what is their least favorite. So yeah, the order is a bit ambiguous. It's not universal, so it doesn't make a lot of sense. And you're putting extra information that is, so you are creating noise in your model. So this information, like for example, the way you order it, this information is something that you decided, is not what the fact, what the data that you collect is telling you. So you're putting that in the model. So you're mixing some noise in there. So not ideal. And also the intensity of classes is ambiguous. So imagine we don't have apple, banana, orange. We have maybe t-shirt sizes, large, medium, small. So, well, we all have experience like this, right? So you buy a large and it become, sometimes you buy a large and it become like super large that is like, it's not supposed, it's not the large that I mean. And sometimes you buy a large and it's like fits really tight, and you'll be like, well, I think it's large, but the large definition is different from the manufacturer and you. So not good. So that's why when you buy clothes online, you check the size guide to check like what do they mean by small, what do they mean by large. I know a lot because I'm from Hong Kong. I know that for Asian clothing, usually like for me, for example, I'm a medium. But like when I came to when I buy clothes from American brands, and like I have to go to a small, sometimes extra small, because the medium, large, and small like are different in different countries. So yeah, like the intensity is really ambiguous. What large do you mean by large? How far from medium is large? Like, so yeah, what do you mean? Like, is ambiguous. So like, what should I put a number there? So for example, you can label them like for t-shirt size is quite easy. Maybe you can measure like the measurement from you know in the middle of it, like how wide is the chest measurement. Okay, so you then put measurement there instead. So okay, that's good because there's no ambiguity. That is the numerical is very standard, pretty standard, so it's fine. It's better than large, medium, and small. But what if is like, for example, this is the happiness. It's like you're very happy, you're happy, or you're not happy. So you got that in surveys, right? You pick it, and then how far is very happy to happy. So if happy is 10, so is very happy 100 or very happy at 20? Yeah, so yeah, it's very, very ambiguous for categorical data. So it's difficult to convert it back to numeric to make it make sense. So hmm, yeah, both of them are not very good. So what should we do? Well, some people think of other ways. Some think of counts labeling. For example, if I labeled people vote, let's say like people vote for a party. So I have a bunch of people living in this district, and we do a survey like what party they are going to vote for. Um, so some people say, oh, maybe we can label them by like how many people are supporting them. So that's one way. Or there's a variation of these, and it's just okay. We just order them by which party got the most support, and then we order them like maybe 1, 2, 3 like that. Um, the thing is, both of them have some problems. Well, for the ordering, of course, like they still got the ordering problem because there may be one party that like 90% of people supported, and then the second one is like 9%, and the rest is one. So the intensity is not even as well. So for the actual count, it may represent that. Also, you can do a proportion because you can like, okay, it's confusing. I just divided by the total, so it will be in the percentage, so it's fine. But both of them, all of them actually have a problem that the data, you have to carry this statistical analysis as a whole. So you carry this data as a whole. Sometimes, so you're injecting some information that you drawn from the actually analysis that you have drawn from this data. Um, so this becomes tricky when you apply in real life, because you have, remember, we have the train test split. So the idea the ideal will be like for each record of data, I can treat it as an independent entity. So when I do a prediction, I just, because because when I do a prediction of using the model to do a prediction, I would only receive one entity, and then I would base on that one entity to give the result. So ideally, when I train the data, so each entity should be viewed as individual. But when I do this encoding here, then I am drawing a conclusion from the statistical distribution of the data. So it's not like purely based on one record of the data, and that's very tricky, uh, especially if you have the train test split, that your train data actually has one demographic and then your test data is not. Well, you can kind of try to minimize this effect um, by randomly picking your test data and make the split. This will help, and hopefully if you have enough data, the demographic will keep on the same, so it doesn't really affect it as much. But there's always a chance that when you get new data coming in, then this statistical um, conclusion is not valid anymore, then it will not work. So be very very careful if you want to create like be creative and do things like that. That's also a downside of it. um so well, yeah, maybe regression is not best too, because like it's so difficult to work with categorical data. What if like I have an algorithm that I just deal with categorical data as a category? Well, actually, there are some things that actually designed to work with categorical data. Like for example, decision trees. Decision trees is I will explain a little bit here. It will be a short episode today because I've been like busy with hi, hey, hello. Someone say hello to me. TDC. Yeah, yeah. Your name is a little bit difficult to pronounce. So I just gotta pronounce TDC. The first three letters of your name. Hey, hi. Um, yeah. So decision trees, I will explain a little bit. I would spend time next week diving into like it more. Maybe talk a little bit more about how it works, and I don't know like how much I could dissect it, and but I would also do some practical kind of practice of writing some code. Like I said today, I decided to not write any code and to do a special episode just to give the overview of categorical data. And it will be a little bit shorter because I'm preparing the workshop this Sunday as the data science workshop for with PyCon Africa. So it's for absolute beginner. So we have lots of students apply, and it will be exciting to see that happen. So yeah, so spent lots of time on that. So sorry, I've been carrying away by a lot of other community things, but also try to keep the stream running. So I have to make the balance. Um, okay, so that's decision tree. Neural network, actually, neural network again is it also very like it based on linear algebra, so it works with numbers, but there's some modification of it using softmax activation, then you can get categorical data as a result. I won't dive into detail here. I think I'll save that for when we talk about neural network, and then we talk about. But it just like give you an idea of this, something that is designed for categorical data. A support vector machine. Support vector machine is it's I don't know how to say. It's basically like putting things in categories. So basically, it's just the algorithm itself is a categorical thing, and um, yeah, and also there are other like unsupervised learning techniques that basically just like putting things in categories. So without even like any training data. So yeah, there's actually a lot of different algorithms that work with categorical data. Uh, Better, I would say, or designed for that. So what I want to do now is I want to have a look at scikit-learn, what is available in there, just to give you an idea. That's where you can find those. Okay, so uh, scikit-learn got a lot of base classes that you don't have to worry about because you won't use them. Let's scroll down. So we have some clustering. So clustering again, like is you kind of have some data and you have to maybe reduce the dimension by clustering together. So yeah. But what we want to see is the categorical ones, and And yeah, well, let's see. We do have some, or what I can do is like to click on the thing here. So okay, so what scikit-learn provided is you can actually create some dummy variables here. So it kind of is help you to create dummy variables. And what also scikit-learn provide is that it provides some. I haven't found it yet still. Uh-huh. Where is it? Yeah, so there are others like, for example, neighbors. Like you can do like some nearest neighbors to group things into categories. So it says unsupervised learning, and there are also semi support vector machines here. Yep, so you can see that there are lots of algorithms for support vector machines, and also you can do like classification and regression even. Decision trees is here, so decision trees, and I think they also have random forest, but I think it's hiding somewhere. I have to find it. Maybe it's in assembling model because random forest is an assembling of trees. Um, so yeah, let me see if I can find that multi-classes. Yeah, so there's also like different multi-classes classification algorithm in there in scikit-learn. So yeah, there are a lot of things that you can work with categorical data, even just from things provided by scikit-learn, or because they provide a lot of things, assemble methods. So you see that yeah, you can have like different boosting random forest here, and yeah. So well, you got quite a lot of algorithms to work with, so that's the good thing. Um, so what else? Yeah, so this is a typical decision tree. Um, that actually this is from Wikipedia actually, and this the data you can well I do think scikit-learn maybe like have this Titanic data set here. Let me see if I can find it. So data set loading facilities. Yeah, it got like lots of different data sets. It got a Boston home housing thing. I don't know whether they got Titanic. Let's see if they got the Titanic. It doesn't look like so though. Regressions, yeah. Okay. Or do I? Oh, I looked too far. Sorry. It should be here. Yep. And Iris, they got the Iris data, but I don't know whether they got the Titanic. Yeah, maybe they don't have. So don't worry if you don't have the Titanic data. You can grab it from Cargo. Cargo is, I think, I don't know whether I've shown it before, but like Cargo is a popular site that host competition, and people can, you know, so because there's competitions, so people also provide lots of data that is open data that you can free to use, that you can do your own project with or try to train your own model with. So this the Titanic data. This is like also a popular data to use in teaching. So what they have is like they have this. Let me see if I can see. Yeah. So you have different passengers, and also like so this is the what you want to predict normally whether they survive or not. But it also tells you something about the passenger, the name, which I don't think is super important. Or if you do some very like deep down analysis, maybe about like whether they are related or something, then maybe you can look at the name. The gender of the passengers and age, and also like where they're so what ticket they got actually is like where they're sitting. So some of them are super expensive, so they're first class passengers, and some of them are cheaper. So yeah, classes. So which class they're in. So of course this passenger got like I think 71 pounds or dollars. Like at that time is super expensive because it's a first class passenger. Obviously this person is this yeah, this is a female, it's quite rich. So yeah, survived. So usually, so people found that usually if you're female and if you're in the first class, then you survive. Okay, and also it also label that whether they got siblings or or their families traveling with them. I think. Yeah, maybe I'm just imagining things, but have a look at this data. Is I think, yeah, the link is in the slide, so you can have a look and you can download it. I think the only thing you need is to have a Cargo account. So yeah, which you can sign up for free. Um, so this is a typical decision tree that, like I said, is the passenger a male. So if they are female, then they have quite a high survival rate. But if they're not, they're male, then it will be like about the age, okay? So if the age is below, so yeah, so if they are considered a child at that time, I think 9.5 is how people consider someone a child at that time. Um, yeah, well, it's not like it's far from like being a legal adult, but still, I think the society is a bit different, and yeah, also I think this means that whether they have sibling or spouse, like whether they're family with them, and how many of them. So if you get like if you are very young, even if you're male, if you're very young and got like family with you, so for example, if your mother is with you, the chances are, if your mother bought the lifeboat, like she would hold you in her arms and bring you with her, so you survive. But if you're not, if you're an adult, or if you're alone, then well, not so much luck for you. Just like the movie that we all watched, that like the couple, the main character, the couple there, Rose survived and Jack died. Actually, like Rose was the in the category that like basically she with Daphne, like she's get a very high chance of surviving. She's like a first class passenger and a woman, and yeah, but the thing is like she was on the lifeboat, she just like leave because drama. um but yeah, like so in real life, yeah, in real scenarios, I think like a passenger with a profile like her will highly be asked to board the lifeboat first. So yeah, if you want to check whether the movie is correct or not, you can use this data to write an algorithm to see if it's true or not. And so yeah, this is the basically someone draw a decision tree like that. So an algorithm actually would go through this tree and check, whether a passenger is a male or female, and then like after that, well, the algorithm will be like, okay, if you're female, then I would predict you to be survive, because the chances are there's like quite a high chance that I will be correct, and if not, then I will check the next criteria, and this is how a machine make decision. Um, so and so this is how a decision tree is based on. So which features can help separate? So from the data that I got, from the training data that I got, I would see which feature actually is helping to make the decision. So in this case, after running some experiments, the algorithm running some experiments with the training data, it decided that actually there's a high relation with the gender and the survival. Even the algorithm doesn't know about the Titanic movie or history, right? But or like people's social norm at that time, the algorithm doesn't know. But just like looking at the data, that the test data, that the example that was provided, the training data that's provided, the machine drew a conclusion that okay, gender actually is a high influence on the prediction outcome, which is whether these passengers survive. So this feature will be like the first feature to make decision, and then there's the second feature will be the age, okay, whether you're a child or not. So the tree will also make a decision, and also of course you need to find a threshold of like 9.5 is the age of drawing the line, whether you're considered a child or not. Um, so yeah, so basically from lots of from the data that you provided, a machine can build a decision tree like that. So that's the decision tree, but sometimes, one tree is not good enough because you still got a lot of chances that you guess it wrong, right? Because, well, I'm sure that a lot of females would be like, not able to board the boat because they were too late or they were sleeping or things like that. So it's not always right. So to increase the accuracy, to increase the chances of being right, then you would have to combine this decision making process to draw a better picture of like the results statistically. So so yeah, sometimes you have to so like I don't want to go into too much detail here because that's not my plan for today. But there's two main algorithm here actually do that is the random forest and the tree boosting. So there there are lots of tree-based algorithm that actually that works like that. Based on the decision tree, and I just combine them. But random forest is means that, well, I build a forest. I just like I just build lots of decision trees, and then I combine them to make a more statistically, accurate result, rather than like I just make one decision tree and then it kinds of work, and then but it actually doesn't cover all the cases that there are other, you know rare cases, or there are like cases that, oh, if you're female, but if you're with your husband, then it's maybe things are a little bit different. Or whether you're a first class or third class passenger, maybe a lot of female in the third class still doesn't get out because they can't communicate with people, they don't know the ship is sinking, or when they discover it's too late. So yeah, so it still make it would build another decision trees that cover the other scenarios, and then you combine them statistically to make actually a more general, a broader decision to cover most cases. Okay. Um, Tree boosting is another approach. So it also builds trees, but from each time, that it would also check against the tree that whether it's good or not. Then it would just make a modification is to itself to it's a little bit like trial and error. It's not reinforcement learning. That's another topic. But yeah, but each time, it would just correct from the previous trained tree. So it's called boosting. So boosting is actually from the term bootstrapping. So it's kind of using itself to improve itself. So yeah, so it's kind of like that self-helping. It's like a philosophy of life. You have to self-help. So it's kind of like that. So the tree can help itself as well. So every time you build a tree, it help itself to build another tree. So that's the tree boosting. So yeah, I think that's it for today. So like I said, it's quite short. Sorry about that, because I have to balance my work, my community work, and the streaming. Uh, but like it's difficult to not do one and focus on the other, because I love doing everything and spread myself a little bit too thin. And so sorry about that. But next week, well, we just go slower. We just go slower. We just learn everything bit by bit. Next week we will just go into decision tree and look at like the random forest tree boosting, different type of random forest and different type of tree boosting, and to see how they work. Kind of dissect algorithm a little bit better, and look at what the advantage, disadvantage, any like pitfall when you apply it. Also, I would try to add another session talking about like accuracy and stuff like that, because I think I didn't talk about last time in the logistic regression. I forgot to talk about that, and I don't realize until now that I need to talk about a little bit about accuracy, precise, and recall, and all this stuff. So yeah, I think I will try to add it in next week's tutorial. So yeah, it's not very well planned, because I just plan it on a go. I plan it on a go. That's my style of teaching. So that's why I'm not a certified teacher. I'm just doing streaming, and but yeah, I'm just trying to be to. Well, I would love people to come on and ask me questions. I am more like I enjoy that way much more, and I love people to come and ask questions and discussion about data science stuff and Python stuff. And yep, we would try to do some coding next time, at least use some scikit-learn algorithm, and explore a little bit more. And yeah, I will see you next week, and enjoy. Bye.